Hey everybody, this is Dr. Bricker here with a video concerning Chapter 10. Remember, Homework 6 is actually due on Wednesday, 10/21. We started talking about some of those problems. When we actually meet in person on the 21st, we'll talk about those again, so we'll have some more time. Just, make sure you get a good start on them, and we can finish up whatever you're still working on Wednesday. And then the lab on Thursday the 22nd is an online lab again, so we will not be meeting for lab on Thursday. So no in-person meeting no in-person meeting on Monday. We will meet in person on Wednesday. If you're not there, we'll post the video, and then Thursday is an online lab, so you don't have to come in for that, just as usual. Let's take a look back at a little bit more information from Chapter 10. The energy chapter. Okay, so we've talked about several forms of energy now. We've got kinetic energy. So kinetic energy, 1/2 mv squared. We have gravitational potential energy, which is mg times y. You experienced that with the lab that we did. And we also have spring potential energy, 1/2 kx squared, where k is the spring constant, measured in newtons per meter. And then x is how much the spring is either stretched or compressed. Actually, going back to the first equation here, m is the mass, v is the speed, gravitational potential energy, m is the mass, g is 9.8, and y is the height. Okay, and then again, spring potential, 1/2 kx squared. So k is the spring constant. Kinetic energy, be careful, this is kinetic energy. This is the spring constant. I always write kinetic energy as Ke to avoid any confusion between that and the spring constant. Okay, so we'll use this information to solve some different problems. So when it says conservation of energy, it means the initial energy at some point equal to the same amount of energy later on. The only other thing I would say is we talked a little bit about thermal energy. So the change in thermal energy is the work done by friction. Really, it's the magnitude of the work done by friction. Okay, so this would be kinetic friction and then times the distance that we go through. Unless they tell you otherwise, assume there's no friction. But if there is, some of that energy goes into thermal energy. Okay, excellent. So what you see here is, I want to give you my take on it. Down here, this would be the final amount of energy that you have. And again, you don't always have all of these different parts. This is kinetic energy, gravitational potential energy, spring potential energy. Any thermal energy that you end up with had to come from somewhere, and it comes from how much you started with. So this is kind of like balancing your checkbook. So when it says my take, really that's what it means. You have a total amount of energy to begin with. You have to have the same amount of total energy later, but it could switch forms. Okay, you don't always, again, have to have every different part of this. Here you're starting with kinetic energy, gravitational potential energy, spring potential energy. Maybe one or two of those are zero. Later on, you have to account for all of this. So you either have to have it in the form of kinetic, gravitational potential, spring, or maybe if there's friction, some sort of thermal energy. So really, we're going to be looking at before and after scenarios when we talk about conservation of energy. Now, this is a little bit easier, in my opinion, than momentum. Momentum is a vector. You would have to conserve momentum in the x direction, do the same thing with the y direction. Energy is just a number. It's just the total amount that you have. Regardless of the type of energy, it's measured in joules. So here's an example problem. A car sits at rest at the top of a hill. A small push sends it down the hill. After its height has dropped by 5 meters, it's moving at a good clip. Write down the equation for conservation of energy, noting the choice of system, initial, final states, and what transformation has taken place. Okay, so let me just draw something like this. Top of a hill, we start here, and then we're going to drop down by 5 meters. Okay, I'll just look at the center of this. Okay, so this distance is y. That's the 5 meters. Okay, so when we began, we were at rest, we just had gravitational potential energy. Once we've dropped down by 5 meters, now we have kinetic energy and gravitational potential energy. So we've taken some gravitational potential energy and turned it into kinetic energy. That's the transformation that takes place. Now you could set your reference point to whatever you want to. I'm just going to say, like, this point here, this is where the gravitational potential energy is 0. And again, you're free to set the 0 point wherever you want to. We just are looking at the difference in energy, not a specific quantity at a certain point. We just want the difference. By difference, I mean we went from this height to this height. That difference, the height there, is y. Okay, so maybe I can call this energy 1 at that point, and then I can call this one energy 2. So conservation of energy means energy 1 is equal to energy 2. Now, energy 1, we just have gravitational potential energy. So gravitational potential energy at 1, and it's not moving there. Then eventually you hit it, and now we get gravitational potential energy at point 2, but we also now have kinetic energy at 2. Okay? So you can see, based on what we did before, you don't always have all parts like spring potential, work by friction, that sort of thing. So we took gravitational potential energy at position 1, and we still have gravitational potential energy at 2 relative to the ground down here. But I'm just saying, if I set this at 0 at position 2, this term would actually be equal to 0, right? Because I said that is 0. Okay, so gravitational potential energy turning into kinetic energy for this one. And we'll use that idea to solve a lot of different problems. Okay, let's do one with actual numbers. A child slides down a slide at a constant speed. Okay, constant speed, be careful what's going on here. We're not gaining any kinetic energy. The height of the slide is 3 meters. Write down the equation for conservation of energy. Okay, so kind of the same picture here. This height, I'll just call this y, was 3 meters. We're starting here, sliding this way, and looks like we had some kinetic energy to begin with because we're sliding at a constant speed. So we're just looking at the snapshot of what's going on now. I'm still going to do the same thing. This is position 1, this is position 2. Okay, so at position 1, we were moving. So we had kinetic energy at 1 because they tell us that. And then we also had gravitational potential energy at position 1. Now down here in the ground, I'll call this position 2, we don't have any gravitational potential energy anymore. We just have kinetic energy at 2. Okay, so what else do we have to have at 2? Well, if the kinetic energy didn't change, but we have lost, and I'm putting that in quotes, you can't see me doing it, but if we've lost gravitational potential energy, what could have happened? Well, we must have some thermal energy, right? Or else the thing would have gotten faster. And it didn't. So energy at 2, and I know this because it didn't speed up. What happened to that? We expected to speed up. Why didn't it? Well, some of that energy went into thermal energy. So those are actually equal to each other. Okay, so gravitational potential energy didn't turn into kinetic energy, it turned into thermal energy in this example. Okay, good. Here's another example. While at the county fair, Katie tries the water slide, whose shape is shown in the figure, starting 9 meters above the ground. She pushes off with an initial speed of 2. Okay, so here we have both kinetic and gravitational potential. If the slide is frictionless, okay, how fast will Katie be traveling at the bottom? So at the bottom, there is no gravitational potential energy. So I'm going to say gravitational final is equal to 0. We just have some final kinetic energy down here. Initially at the top, the initial energy, I'll just call it initial energy, was made up of kinetic because they tell us Katie's moving, and also gravitational potential energy initial. Now if you think about this, if you tried to solve this with forces, it would be a really complicated problem. Katie slides down the slide, the angle keeps changing, the normal force is different, gravity straight down, a different part of different component of gravity is going down the incline. You could do this with forces. You'd have to use calculus to do it, though. We can solve it, though, like this. We just know how much energy we start with. It's got to be equal to how much energy we end up with. So the final energy is just kinetic energy. Energy final. And we can set those equal to each other. So the initial energy, I'm going to write it up here at the top. The initial energy is equal to the final energy. Now the initial energy is just kinetic energy plus gravitational potential energy. And then the final energy, the only thing that we have is kinetic energy. So kinetic energy final. So that's the concept I've used, conservation of energy. That's what we have here. Now I've filled in the details a little bit more. Now I can actually put some numbers in. So I'm running out of space, but I will do that right here. So the initial kinetic energy would be 1/2 mv initial squared plus mgy. Y is 9 meters. That's equal to the final energy, which is just kinetic. 1/2 mv final squared. Now if you notice the mass was not given, just to have some faith with this, the mass was not given. Let's put in the details, and now you see the mass actually cancels out because mass is in all the different terms. Okay, now the only thing that you don't know is the final speed. 1/2 mv initial squared, okay, you know all that, plus g times y, okay, good, those are just things you know, is equal to 1/2 v final squared. The only thing that you don't know is v final. You'll have to do a little bit of algebra, but you can do that to figure out v final. Okay, maybe I'll rewrite it right here. 1/2 v initial squared plus gy is 1/2 v final squared. And then just solve for v final. Okay, not too bad. Really pretty powerful if you think about it, not using forces at all. Okay, let's keep going. So this is a review. Again, we've got kinetic energy, gravitational potential energy, and spring potential energy. Okay? So the last example, we turned gravitational potential energy into kinetic, but it could be a lot of different things. We could turn spring potential energy into kinetic, a whole bunch of different scenarios. Okay, so we'll do some more examples from the homework when we meet on Wednesday. So try them out, and then bring your work with you on Wednesday, and we'll spend a good amount of time on Wednesday working on problems. Now, energy in collisions, we've talked about this in the lab, perfectly inelastic collision. Regardless of the type of collision, the initial momentum is equal to the final momentum. Kinetic energy doesn't follow the same relationship unless it's a special collision. So perfectly elastic collision is the only one where the initial kinetic energy is equal to the final kinetic energy. And that's a special case. This is, again, I don't even like to write it because it's not in general true. It's just true for this scenario. That was the collision where we put magnet versus magnet. We let them collide. It was a nice gentle collision, and you saw that we lost a whole bunch less kinetic energy in this collision compared to the stick-together type. Okay, let's actually take a look at this one. We saw this one before when we talked about momentum. So here we have a couple of train cars moving towards each other. So look back at the Chapter 9 notes. We did this momentum part before. So mass 1 came in with 1.5 meters per second to the right. Mass 2, which is twice as massive, moving to the left at 1.1. They stuck together and they moved off to the left at 0.25 to the left. That's what the minus sign means. So we actually solved this before. This was from Chapter 9. Look back at the notes. And we solved this by saying that the initial momentum in this situation was equal to the final momentum. That's how we solved for this amount. Let's actually look at the kinetic energy and see how much thermal energy was created. In other words, how much kinetic energy did we lose? It had to go somewhere. It went into thermal energy. Okay, that's a synopsis of what I've said. So initially, here's the kinetic energy made up of both of them. 1/2 mv1 squared plus 1/2 mv2 initial squared. So we started with this amount of energy. Once they stuck together, we could figure out how much kinetic energy the group had, and that's what we have here, 1900. So 4.7 times 10 to the fourth. 1, 2, 3, 4. 1, 2, 3. 47,000 joules. Now we're down to 1900 joules. That's a lot of joules that we've lost. We haven't really lost it. We don't have it in terms of kinetic energy anymore, but it became thermal energy. So the difference between 47,000 and 1900, where'd that energy go? Well, it went into thermal energy. The metal got deformed, actually heated up, that sort of thing. And there you see the amount. 96% of the initial kinetic energy is transferred into thermal energy. Now, sometime in the 1800s, people took a couple of trains and ran them into each other. They sold tickets for this event, actually. They got them going full speed. They ran into each other just to, as a spectacle, and several people were actually killed. They didn't anticipate how much energy they would have. It was like a big explosion going off. Okay, so again, momentum was conserved in this example, but kinetic energy definitely is not even close. Okay, a little bit about perfectly elastic collision that we did before. So this is the one again where it was magnet to magnet, and we had one mass moving, the second one was stationary. They collided, and that's what we have here actually. This is mass 1 colliding with mass 2, and they actually bumped off each other. Like one went one way, one went the other. So mass 2 was not moving initially. So this statement is conservation of momentum. Now, if it's a perfectly elastic collision, kinetic energy is actually conserved too. We can predict what the speed of 1 and the speed of 2 will be after the collision, and we can come up with that from this relationship here, from both of these actually. So what I want to know is, what is V1 final? Whoops. What is V1 final and what is V2 final? Just based on the initial speed of 1, so just knowing V1 initial and their masses, I want to be able to predict V1 final and V2 final. And you could actually do that because we've got two equations with the same two unknowns. So the way to do this would actually, solve for V2 final, say in this equation, and then plug it into the other equation. It's a little messy mathematically, but not too bad. When you do that, you get this set of equations. So again, what I wanted was to predict V1 final and V2 final just based on V1 initial and knowing the masses. And that's what I have here. So the first equation that you see here, I'm just going to call it equation 1. V1 final is M1 minus M2 divided by M1 plus M2, and then the whole thing times V1 initial. And then the second one, I'll just call this equation 2 down here. V2 final is 2M1 divided by M1 plus M2, and then times V1 initial. So I have what I wanted. V1 final just based on V1 initial and the masses. V2 final just based on V1 initial and the two masses. Now, if you remember, when the carts in the lab had about the same mass 1 came in, we actually called it mass A, interacted with mass 2, which was initially stationary. When they had roughly the same masses, the first cart stopped and the other one went on. And that's what would happen here. If you notice, if they have the same masses, let me change the color of this. If they have the same masses, mass 1 and mass 2 are equal to each other, V1 will stop. Now again, if they have the same masses, 2M1 divided by, really, 2M1 again, because M1 is equal to M2, V2 final would be equal to V1 initial. And you saw that too. If they had roughly the same masses, the first one coming in would stop, and the second one would continue on with the same speed that the first one had. So these equations actually show you that that's true. Now, if mass 2 was bigger than mass 1, that's what we actually did in the lab, the first mass would turn around and go back the other way. And you see that that works too, actually. Let me go to a third color. When M2 is bigger than M1, V1 final is negative. And that's the scenario that we actually did. We made mass 2 bigger than mass 1, and then once they collided, the first mass went back the other way through the gates. Its speed was equal to, it was a negative speed. Okay, so the lab that we did with collisions, this really explains the behavior of the elastic situation. Okay, pretty cool stuff. That's the one that always gives me goosebumps. So we will do 1056 on when we have class on Wednesday. So there's a little bit about power, how fast you can do work. So remember, work is the change in the amount of energy that you have. Power is how fast you could actually do that. So in my on my bicycle, I could get up to 20 miles per hour. In my car, I could do it a lot quicker. So my car is more powerful than my bicycle. When I run into the tech building, I could either take the long way up and end up at the top of the steps, or I could run up the steps. Regardless of either path I take, when I get to the top, I have the same amount of I've gained the same amount of gravitational potential energy. Just if you run up the steps, you do it a lot quicker, so you need more power to do that. It's the same amount of energy, you just do it a lot quicker, so it's more powerful. So it's the rate of change of energy. That's what power actually is. You can see that here. So this would be joules per second, and it's called something else. It's called a watt. Oh, you can see it down here actually. So a joule per second is a watt. How fast you could actually do work, or how fast you convert energy from one form to the next. Okay, so this is a watt. Okay, I think I threw in 1 or 2 problems on power. Okay, you probably have heard of horsepower for cars. And the SI unit, though, is a watt. So whenever you see watt, immediately think, oh, that's a joule per second. That's the more useful way of thinking about it. Okay, there's another thing called output power that's based on the force. So if you have work, that's what this is, work per time. You've seen earlier in the chapter that work is force through a distance. So F times delta X, and I still got the delta T part. So this is work. You could rewrite the equation like this. So force times delta X over delta T, which we know that is the speed. So force times speed ends up giving you the rate of energy transfer due to a force on an object moving at a speed. So it's almost kind of like an instantaneous power. So force is Newton, velocity is meter per second, so this turns out to be joules per second unit-wise, so it works out too. Yeah, why would you ever multiply force times velocity? Just think of the units. Velocity is meters per second, so really then it's newtons times meters divided by second, and then that's joules per second. Okay, good. So you got all the background information for chapter 10 now. Try working on the homework problems. There's some good examples in the book too. And then Wednesday, first thing, we will start with homework problems, and then time permitting, we will go into the next chapter, which we actually go back to chapter 6. Okay, see you Wednesday. Email any questions. Talk to you soon. Bye-bye.